Hello, so I'm sitting here trying to review the second order central difference, so I figured out I might as well do a video. All right, so let's see. We have, this is how we're gonna do it. I just reviewed it. So you have a function, right? And then you want to look at a little bit to the right of that function. And you're going to use a Taylor series expansion to express this, because you don't know the value of the function. You just know discrete values, right? So what you're going to do is you're going to say, well, I can evaluate my function at that point, and then if I get the slope and I multiply it by this interval, then I get an approximate value of the next point at x plus delta x of my function, right? So that would be, I'm going to multiply delta x by the derivative of that function with respect to x. That would be my slope, right? And then I can just keep doing it for better precision. So this would be a second derivative, and this would be divided by 2 factorial. And then you would keep going and going and going. Now, we could do a similar process if we wanted to estimate a value on the left of our current value. So what would change? Well, essentially, all the terms that have an exponent that is odd, including this one that has an exponent of 1, would have a negative in front, right? Plus higher order terms. Right, so let's call this equation 1, and I'll call this equation 2. Now, what we can do is we can add 1 and 2. Now, at first when I saw this, I thought, why would I ever want to do this? Well, if you're trying to solve for a second order derivative, if you add, you're going to cancel these two terms because they have opposite signs. So that's a good insight. So let's add them together and let's see what we would get. Well, here we would get f of x plus delta x plus f of x minus delta x right here equals what? Let me make this a little neater for you guys. Equals what? Well, now that's equal to 2 times f of x. This term cancels out, which was the whole point of doing this. And then I would get plus 2 delta x squared over 2 factorial, which is just 2, times delta, second derivative of the function f. I don't know why I'm writing so bad. Second derivative of f with respect to x plus the higher order terms, which we will truncate. And keep in mind that we will have an error. So the error can be quantified on the order of, and this is how you say it, delta x to the third of the highest order term that didn't get included. But now, this is like having 0 here at this point. Now we can solve for our second derivative. So what would we get? Well, we would get delta second derivative of our function with respect to x is equal to f of x plus delta x plus f of x minus delta x right here. And let me make this a little bit better. Minus, actually, bring that 2 to the other side, f of x. And then these 2's would cancel out, and we would have delta x squared in the denominator here. And this would be our result for the central difference. Actually, I'm going to write it in a different way as well. And then you could put this in your code if you were trying to estimate the second order derivative using perhaps an iterative method. So this would be f at I plus 1 plus f at I minus 1 minus 2 f divided by delta x squared. All right. Well, that was a good review for me. I hope this was good for you too.